going to tell us is it's going to tell us the energy level of the electron that we're talking about. The potential values that you can have for n, so the lowest value that you can have is n equals 1, and it's going to go up by plus 1 each time. So you can have 1, 2, 3, and then so forth. You also want to know what these mean. So if you have an n equals 1, that is the closest that you're going to get to the nucleus. And the more you increase this n value, the further away you are from the nucleus. So that's what that interpretation means for that. Now n is really important because when we look at L and M sub L, those are all going to be related to your potential n value that you start with. So that's n. L is the next one. L is called a couple of different things, so sometimes I've seen it called the secondary quantum number. I've also seen it called the angular momentum quantum number, but they mean the same thing. What this is going to tell us is it's going to tell us the subshell of the orbitals that we have. Now these words get mixed up a lot, so subshell and orbital. Subshell represents the collection of all potential orbitals that you have. So for example, if I'm talking about the p subshell, there's 3 orbitals that are related to that. And we'll talk about that when we get to n sub L in just a minute. But when you see subshell, that means a collection of orbitals. The possible values that you can have for L, so the lowest value that you can have here is L equals 0, and again, just like n, you're going to go up by plus 1 each time. You can have L equals 0, 1, 2. The highest value that you can end up with is equal to n minus 1. So for example, if my n value is 4, the highest L value that I could have is 3. So that's the way that you would interpret that. Now L is a little bit important because we also have to be able to interpret what each of these individual L values mean. So we'll look at the first couple because those are going to be the important ones. So if we start with L equals 0, that's going to tell us that we are in the S subshell. The other thing that I want you to know here is what the shape of these orbitals are going to look like within that subshell. So S is very easy, so S is just going to look like a sphere or a circle. So that one's pretty straightforward there. The next one is L equals 1. That means that we are going to be in the P subshell. Now these ones are going to look generically kind of like a dumbbell. Something like this. Now you might see it drawn a couple of different ways, and we're going to get to this in just a minute. You might see it draw straight up and down like this. You might see it sideways, you can see it at an angle, but you're looking for the shape. The orientation doesn't really matter too much for this class. You're looking for that dumbbell type shape. And we'll talk about why we have 3 of them in just a minute. So that's L equals 1. L equals 2 is probably the last one that I want you to think about the shapes for. So that's the D subshell. Now this one's a little bit weird, and I don't even really know if you'd be asked this, but I want to cover it for completeness. The generic shape that you're going to see for a d orbital is going to look like a clover. But the d is a little bit weird because there's 5 total d orbitals that we have. 4 of them are going to look like this. There's one that doesn't quite look like that. The other one kind of looks like a p orbital with a ring around it. But in general, they're going to look clover shaped. Like I said, I don't know if you'd be asked that, but I just want to make sure I cover it for completeness since I did it for the other ones. You can go higher than this. Like we might talk about L equals 3. We're not going to ask you about the shapes of that. So L equals 3 would be the F subshell. But they're very complex, so we're not going to look at that. So what you really need to know here is you need to know if you're given an L value, you need to be able to translate that to what subshell that you're in, and vice versa. So for example, if I tell you we have a p electron, you have to kind of relate it back to this and figure out that L equals 1. So you need to be able to convert between them, and you also need to know what those shapes look like. So that's L. The next one that we have is M sub L. This is usually called magnetic quantum number. Now what this one tells us is it tells us which orientation that we have in space. It represents the orbital's orientation. So, let's talk about the possible values, and we can actually relate that to something that we just talked about up there. So the potential values that you can have for m sub L is it's going to range from minus L to positive L, and it's going to go up by 1 each time. Up by increments of 1. Okay. So I want to show you something quickly here. So if we go back to this example that we talked about with the P subshells, let's think about the m sub L values that we could have for that. If we did the possible m sub L values for the P subshell and L is equal to 1, we could have 3 of them. We could have -1, 0, and +1, based on the rules that I just wrote here. That's why here we have 3 different orbitals, because each one of these m sub L values correlates with a different orientation of the orbitals in space. Now you don't need to know that part, like you don't need to know which orientation corresponds with which m sub L value, but that's what the connection is, because we have 3 different orbitals, they're oriented differently, and that's what this will tell us here. Another thing that's useful that can come out of the m sub L values is if you add up all of the m sub L values, or you count the number of them, that will tell you the number of orbitals. So here, when L equals 1, I have 3 m sub L values, I have 3 p orbitals. If I did it for the D subshell, I would have 5 of them because L equal to 2, and that's why we have 5 different orbitals there. So that's the other thing that m sub L can tell us. The last one is by far the easiest. So this is going to be our spin quantum number. So the first 3 are kind of related to each other because they all kind of depend on results from the previous one. Spin quantum number, so m sub s, just has 2 potential values. It can either be positive or -1/2. And that just refers to if the electron is pointing up or down. So this one you don't really have to do too much memorization for, you just have to know that it can be positive or -1/2. The other 3 though, you do want to be able to know those. Any questions on any of this? Do you guys want to see an example of a problem that deals with quantum numbers, or do you feel like just trying some right now?
See one.
Okay, let's do a quick example here. I'll also give you a chance to show you one other thing about quantum numbers. So my example here says, what are the possible quantum numbers for an electron in a 3p orbital? Okay. So what we want to think about right away is the type of orbital that we're in. So we're in 3p. So I didn't necessarily write this when we were talking about it before, but when you see this orientation here, the number that comes first, that's your n. And the P is related to L, so it's telling you what subshell that you're in. That's why over here I wrote out the different possibilities and what that correlates with here. So if we think about the possibilities that we can have, so we know our n value is fixed. N has to be equal to 3 in this case, it can't be anything else because they're telling us the energy level right up front. L is also fixed here because they're telling us that we are in the P subshell. If we're in the P subshell, L has to be equal to 1. So that can't change as well. Now the m sub L values can change. So here we could have 3 possibilities depending on what the orientation is of that p orbital. The possible m sub L values that we could have are -1, 0, and +1. And then my m sub s values could be either +1/2 or -1/2. Now I'm not going to write all of these out, but if we think about the different possibilities here, I could write out a couple of them. So we could have 3, 1, minus 1, and then plus 1/2. Could also have 3, 1, minus 1, negative 1/2. And then just 4 others. You could do 3, 1, 0, plus 1/2, and then or minus 1/2. And then you could also do 3, 1, plus 1, 1, plus 1/2, minus 1/2. So I'll just write plus 4 others here. So that's how you would go about something like that. Okay, so let me hand out the worksheet for today. So what I'm going to have you guys do is the front side. So the front side are all quantum number related questions. They should go fairly quick, so maybe 5 or 10 minutes. Yeah, we finished that last worksheet. So we actually ended up skipping weeks. That one took 2 weeks. I would looks like most people are finished up, so let's go through these ones. So number one, and what you're trying to figure out is you're essentially being asked if that pair of quantum numbers can exist. So for this one, I'm only going to talk about the ones that aren't valid. So the first one is valid. There's no issues with that combination there. 2 does have a problem. So 2 is not going to work. Does anybody know why that second one isn't going to work? What about that set of quantum numbers is invalid? Yep, you can't have that L value here because your N value is 1. Your L value, the maximum value that you can have is N minus 1. So here they're equal, we can't have that. So invalid L. 3 and 4 are actually good. So those are valid as well. The last one also isn't going to work. So what's the issue with the last one? Yep, it's M sub L. So our N value is fine, our L value is fine because it's 3, which is N minus 1. The M sub L value is what's not going to work. Because remember, M sub L ranges from minus L to plus L. Here, 4 is greater than the maximum value that you could have, which is 3. So no, invalid M sub L. So that's the answer for the first one. So the second one, how many orbitals are in each subshell? So I did mention this briefly. But if you want to think about the total number of orbitals that you have within a subshell, you want to think about the total number of M sub L values. Alternatively, you can just memorize it, but it's based off of the M sub L values. I'm just going to think M sub L. So for the first one, if we have the S subshell, that would be L equals 0. The only M sub L value that you can have for that is 0. So I have one M sub L number here, so that means I have one orbital. Make a little bit more sense for the second one. So if we're talking about the P, L equals 1, my M sub L values again range from minus L to positive L. I can have negative 1, 0, positive 1. So I have 3 total M sub L numbers that I have here, which means that I have 3 orbitals. You can do the same exact thing to figure it out for the other one. Just write out all of the M sub L values or memorize it. So for the D, it's going to be 5, and then D, it's going to be 7. So that's number 2. Number 3 is related to number 2. So I didn't say this explicitly, but I'm definitely hoping that you picked this up in class. Remember, each orbital can hold 2 electrons in it, and we'll see that when we do the orbital diagrams in just a minute. So if we think back to our answers here, we already figured out the number of orbitals that are in each subshell. We know the fact that each orbital can have 2 electrons. Essentially, we're just multiplying these values by 2. So for the first one, I have 1 orbital. That 1 orbital can hold 2 electrons. So the maximum that I can have is 2. For the P, again, I have 3 different orbitals here. Each one of the orbitals can hold 2, so 3 times 2 is 6. And then for the D orbitals, it's 10. And for the F, it's 4. And we're going to see in just a minute when we do the electron configurations, this will actually match up very nicely. So that's the answer for 3. Now 4 was a little bit tricky. So again, you have to pay attention to how these questions are worded here. So it says, how many electrons are in each orbital? So the answer for that is 2 for all of them. If we're talking about an orbital, that can only hold 2 electrons. If it's a subshell, the subshell represents all of the orbitals, then you can hold more. So again, just be careful with the wording for stuff like that. Anything else on quantum numbers before we move on? So the next thing that we're going to talk about then are electron configurations. Now again, this is something I'm also going to go through fairly quickly because I know that you've seen it already. We just don't have enough time to do this completely from scratch. Make some room over here as well. So there's actually 3 different ways that you guys need to know how to represent electron configurations. The full one is the first one. second one is the noble gas configuration. And then the third one is the orbital notation. So I'm going to show you guys an example for oxygen to show you all three of these and what they look like. We'll look at an oxygen atom. Now that if you're really struggling with electron configurations, normally what I would have people do is if you're just not getting the hang of this, try to write out all of the first 10 elements. Because once you do that, you'll start to see what the trend is. You essentially are counting up by 1. So for example, if I just show it here for oxygen, we count up by 1. So 1s1, 1s2. S orbitals can only hold 2. 2s1, 2s2. 2p1, 2p2, 2p3, 2p4. So again, the full electron configuration is just going to be all of that I just said. So it's 1s2, 2s2, 2p4. So again, like I said, if you're really struggling, write out the first 10 or so and it'll start to click what the pattern is there. For the noble gas configuration, what we're going to do is essentially we're going to condense some of this. Now it's not really clear in this example why it's going to save that much time, but when you get to some of the longer electron configurations, this saves quite a bit of time. Now the way that you're going to figure out the noble gas configuration is you're going to look in the row where your element is. So here, oxygen is in this second row here. What you're going to do is you're going to look at the row above that, and then you're going to look in the noble gas column and see which noble gas is in that column. So here, oxygen is in this row. If I look in the column in the row above, I have helium here. What we are essentially going to do is we're going to abbreviate some of the electron configuration with whatever that electron configuration is. So for example, here, 1s2 is the same electron configuration as helium. So what we're going to do is instead of writing 1s2, we're going to write helium. Like I said, it doesn't save a lot of time for this particular example. When you get to the longer ones, doing this is going to save quite a bit of time. And then what we have left over is 2s2, 2b4. So that's the second way that you can do it. Pay attention on the exam to how they're worded. So if they ask you for the noble gas configuration or the full one, just make sure that you follow the instructions. If you know how to do one of them, I'm sure you know how to do the other. The last one is orbital notation, and this one's a little bit different. So for this example, I'm going to write out all of it just because it doesn't really take me too long to do so. But typically when you do orbital notation, you're only going to draw the last, kind of the highest energy orbitals that you're working with, because all of the ones before that are going to be filled. So for this example, the 1s and 2s are going to be filled no matter what. We don't really have to worry about how we do that. The only thing is with the electrons, make sure you have one pointing up and the other one pointing down in each case. Now the 2p, we do have to be a bit more careful on how we do these ones. So the 2p one is the last one that we have. That's probably where the interesting stuff is going to happen. So the way that you want to place these remaining 4 p electrons here is you want to place one in each orbital first, and then once every single orbital has one, you can start pairing them up. The other thing as well is you want to point them in the same direction. So for example, if I start with the 2 p's and I start by pointing some of them up, like this, you want to make sure that they're all pointing up. That's going to be the easiest way to do it. And then with the last one, now we have one more that we need to place, then you can start pairing them up. So that actually becomes very important for the next definition that I want to give you. So usually we're going to use orbital notation to figure out if something is paramagnetic or diamagnetic. You could technically figure this out without doing the orbital notation, but usually it's easier for most people just to do it. So paramagnetic is going to mean that we have some unpaired electrons in our orbital diagram here. Unpaired electrons. Diamagnetic means that every single electron is paired up. So in other words, one of them is pointing up and then one of them is pointing down. This is also where you can make mistakes if you're not careful about following the rules that we just talked about before. So this is the correct orbital notation here. If we were to classify this one, we would say that this one is paramagnetic because I have two unpaired electrons here. But I'll show you in just a minute how you can make a mistake, and that's going to cause your orbital notation to be wrong, and you also get that characterization wrong. So let's say we were doing it again, and we're just looking at the two P's, and let's say I forgot the rules that I told you before when we were pairing these up after every single one has one. If you forgot about that, you might end up doing it like this. You might draw your diagram like this. That's a problem because A, this is wrong, this is incorrect, and B, you would also characterize it wrong. Because if you look at this orbital diagram here, we would say that this is diamagnetic because I don't have any unpaired electrons in this diagram here. So that would also cause that answer to be wrong. So that's why you have to be careful when you're doing this step here. Make sure that you follow those rules and you do that correctly, because that can cause other things down the line to be wrong. Are there any questions on that? Okay. So one other thing that I want to bring up before I have you guys try some are the exceptions. So these are a little bit trickier. So the first one I'm going to talk about is half-filled, completely filled d orbitals. Okay. So I think this is easier just to show you guys with an example. So let's say we were doing this for chromium. If we just follow these basic rules that we talked about before and we didn't know anything about the exceptions, we would write the electron configuration as follows. So I'm just going to write the noble gas version. We'd write it Ar 4s2 3d4. This is what we would expect if we just counted up on the periodic table, similarly to how I did for the oxygen example. But this isn't actually the electron configuration that we see. What we see is, in practice, this s electron is going to move into the d orbital. Now the reason for that is because if we have a completely half-filled set of d orbitals, so that would be a d5, or a completely filled d orbitals, which would be d10, those are going to give us extra stability. So when I'm talking about half-filled, I mean d5, completely filled, I mean d10. What you want to watch out for if you're worried about encountering something that's going to look like this, you want to look for something that ends in d4 or d9. Because that means you're pretty close to one of these two stable configurations that we have here, and that means that one of those s electrons can move to make that happen. So the electron configuration that we actually see for chromium is, like I said, one of these s electrons can move to the d. So it'll be 4s1, 3d5. And that kind of goes against the rules that we've talked about so far. So like I said, what you want to watch out for is something that's ending in d4 or d9, because that means that you're really close to a d5 or a d10. So that's the first one. The second one isn't really an exception, but just something that you need to be careful of, and that's going to be writing the electron configuration for transition metals, specifically for their ions. And again, these two can be combined as well. So you can combine this step also with one where you have to change the base configuration as well. So there could be questions where you have to think about both of these things at once. So let's say we had something like iron 2+. So let me first show you what the base configuration is for just a normal iron atom. It would be Ar 4s2 3d6. Now when you form the ion, you actually take away the electrons from the s orbitals first. That's what you want to be careful of. Even though we end in d6 here, you want to take them away from the s first. Take electrons from s before d. So for this particular ion, if I want to form iron 2+, I need to take away 2 electrons. Those electrons are going to be taken from the s2 that I have here. The Ar 3d6 in this case. Any questions on either of those two? Okay. So then what I'm gonna have you guys do is do the second half of that worksheet. So there's a bunch of electron configurations there. If you feel pretty good about the first one, you don't, or first two for that matter, you don't have to do all of them because that's just writing electron configurations, but just do the amount that you feel like you need practice for. But I definitely want you to try 3, 4, and then 9. Alright, so I'm going to go through the answers here. So I'm just going to write out the first two. So these are going to take me a little bit to write out just because some of them are a little bit long. But I'll put all the answers for the first two on this side of the board here. Alternatively, you can just Google the electron configuration. So the ground state, they'll give you that right on Google. Those are the full electron configurations, and then the noble gases, question 2. And we'll write those here. So those are all of the electron configurations there. Again, make sure for the exam you know how to do both. Even these longer ones, they might be tedious, but still practice a few. Make sure that you know how to do that in case you have to. So for 3, we have to figure out the electron orbital notation for the ground state of fluorine as well as its ion. So fluorine and then its ion, you have to know what that is, that's F minus. So what I would recommend doing is writing out the electron configuration for them. So for fluorine, it would be 1s2, 2s2, 2p5. And then for F minus, so again, if we're adding if we have an ion here, we have a minus charge. So effectively, we're adding an electron here to our configuration. So the electron configuration for this ion would be 1s2, 2s2, 2p6. Again, we have a minus charge, we've gained an electron here. So I'm only going to show it for the p orbitals, just because the 1s and the 2s are going to be completely filled no matter what. But the 2p is where we're going to have some differences between them. So again, remember how you want to do this. You want to do one in each orbital and then start pairing them up. And make sure that you have them pointed in the same direction. So I'll start with this top one here. 1, 2, 3. Now I can start pairing them up. 4, 5. For this one here, same thing. 1, 2, 3, 4, 5, 6. So that one will end up being completely filled. Now I didn't ask you this, but you also could have figured out paramagnetic and diamagnetic based on this. So this one would be paramagnetic because we have that one unpaired electron. This one would be diamagnetic. So that's how you'd go about that one. For number 4, it's asking us for the noble gas configuration for magnesium and its ion. Again, we have to know what its ion is. Magnesium is 2+. So the one for just base magnesium here is neon 3s2. And then when we form the ion, if we have a positively charged ion, we're taking electrons away. So we're taking electrons out of that configuration. Here we need to take away 2, so then we get just neon by itself. So that's how we would go about that one. 5 is probably the trickiest one here. So this one's quite a bit tougher. So this one asks which ion is paramagnetic. So what I would recommend you do for this one is figure out the electron configuration. If you're not able to tell just by looking at the electron configuration, you can always write out the orbital diagram. You don't have to, you can usually just tell by looking at it. So we'll start with palladium 2+. So its electron configuration is going to be krypton 48. So the answer actually is this one, but I want to show you why the other ones are incorrect. So this one is paramagnetic, because again, not all of the d orbitals are going to be filled. You can draw out those 5 d orbitals and place those electrons, you'll have 2 unpaired electrons there. Copper plus, and the other one that's tough in this problem is silver plus. This is where you have to be very careful, and this is where we have to think about both of those exceptions that we've just talked about before. So if we write, so let's start by writing just the electron configuration for copper. This is one of those exceptions. So this one is going to end in 3d9. Again, if we're close to a d5 or a d10, we want to be able to do that. So the electron configuration for copper on its own is argon 4s1 3d10. So before you even worry about the ion, figure out what the base configuration is. So this is one of those exceptions. And then when we figure out the ion, we have to remember that second part, that we take away the s electrons before the d, because both of those errors would cause this one to be wrong. So if we take away the s electron, we're taking away 1 here. This causes it to be Ar 3d10. And then we'd have completely filled d orbitals, so that one would be diamagnetic. So that's why that one is that. Calcium 2+ was a little bit easier, so its configuration is just argon. Everything will be completely filled there. Silver is another case just like the copper one. Again, figure out what the base configuration is first. So again, this is another one that's going to end in D9. It's just a row below the copper one that we did before. So just silver on its own would be 5s1 4d10. And then when we form the ion, we're taking away 1 electron, we take away the s before the d. So what we get here is krypton 4d10. So that's why that one is diamagnetic. So I gave you a little bit of practice kind of applying both of those difficult rules that we did before. That's also where we'll stop for today. We don't really have time to do anything else. If you do have any last minute questions that come up, feel free to see me in my office hours tomorrow or send me an email.